Okay, hi guys. So in this lecture, we'll be starting off with some practice on the iodometric titration. So let's get started. So the first question is a 1 gram sample containing Na2C2O4 Na2C2O4 molarity is given 12.6 is titrated with. So this is not just related to iodometric titration. We are doing the practice on titration in general. Is titrated with 40 ml of 0.02 m KMnO4 solution. Okay, in acidic medium. Okay, so the ionic reaction is also given. Is C2O4 2 minus plus MnO4 minus plus, let's say we have some H plus also, goes to CO2 plus Mn plus 2 state and H2O. So let's balance the equation. We'll have 5 here, 2, 16, 10, 2 and 8. So this is the balanced equation. Okay, so you have to calculate percentage of Na2C2O4 2 minus, or not 2 minus, we have put the Na2 here in the sample. Okay, so this is the question. Please take some time understanding the question, then we'll be starting off with the solution part. You can pause the video, you can design your solution, then you can just compare it with the solution which I am providing you guys now. So as you can see that we have 40 ml of 0.02 m KMnO4. Okay, so we can say that millimoles of KMnO4 would be equals to molarity of KMnO4 into volume of solution in milliliter. Okay, and then we can say that equivalent of KMnO4 would be millimoles of KMnO4 multiplied with n factor of KMnO4 in the reaction. Why we are concerned about milli equivalence of KMnO4? Because in the question itself it is written titrated. So in titration we equate the milli equivalents. Okay, so what is the n factor of KMnO4? So it is going from +7 to +2 state, hence the n factor here would be 5. Okay, so from here we can calculate the milli equivalents of KMnO4. How? M is given of KMnO4, which is 0.02, volume in ml is given, which is 40 ml, and then n factor is we calculated from the balanced reaction, which is 5. So we know milli equivalents of KMnO4. Okay, now we have to calculate the percentage of Na2C2O4 in the sample. That means whole 1 gram of Na2C2O4 sample is not completely comprised of Na2C2O4. That's why percentage is asked. Okay, so this implies that there must be some impurity in the sample. Okay, so let's say the weight of Na2C2O4 in the sample was X. Okay, weight of Na2C2O4 in the sample was X grams. Okay, now we have to equate this milli equivalents of KMnO4 with the milli equivalents of Na2 C2O4 which actually reacted following this reaction because titration happened. Okay, so as a result we have to calculate the milli equivalents of Na2C2O4. And how is milli equivalents of Na2C2O4 calculated? So for calculating mini equivalents, we know that milli equivalents of Na2C2O4 is nothing but would be weight of Na2C2O4 which is present in the sample, which is x grams, divided by equivalent weight of Na2C2O4. Okay, so equivalent weight of Na2C2O4 would be nothing but molar mass of Na2C2O4 divided by 2, as the n factor of C2O4 in the above reaction would be 2. How? It is going from +3 state to +4 state, hence n factor would be 2, because there are 2 moles of C2 also present in the compound. Hence you can calculate the molar mass of Na2C2O4. This is the equivalent weight. So milli equivalent would be, so this is the equivalent, not the milli equivalent. For calculation of milli equivalent, you have to multiply this equivalent with 1000. Okay, so milli equivalent of Na2C2O4 would be nothing but x upon m over 2 into 1000, and equate this to milli equivalents of KMnO4 to get the answer. Okay, let's move on to next question, where we have a solution of H2O2 diluted to 20 times and then was titrated against standard solution of KMnO4, and 10 ml of this dilute solution required 20 ml of 0.1 N KMnO4. So you have to calculate the volume strength of H2O2. Okay, so let's get started with the answer part. So this is the question of titration, so we can directly write that milli equivalents of H2O2 at equilibrium point would be equal to milli equivalents of KMnO4. Milli equivalents of KMnO4 would be nothing but normality of KMnO4, which is 0.1, multiplied with volume of solution of KMnO4, which is 20. Okay, so this is the milli equivalents of H2O2 in 10 ml H2O2 solution. Okay, so this is nothing but so in 10 ml it would be, so we can calculate that normality in 10 ml, normality of 10 ml multiplied with volume of solution in 10 ml would be volume of H2O2 used in the titration would be 10 ml. So n in 10 ml multiplied with 10, I am n just writing 10 as a subscript of n. This just implies the normality of H2O2 in 10 ml solution would be 0.1 into 20. So we can write that normality would be 0.01 into 20. Okay, so In 10 ml, this is the normality. Okay, and we need to calculate normality in, so this is the diluted solution. Okay, so this was 20 times diluted. Okay, so normality, what would be the normality of H2O2 solution then? So we know that normality is nothing but equivalence of solute upon volume of solution. Okay, in liter obviously. So N times V is the equivalence of solute. Okay, so equivalence of solute in 10 ml solution, which is 20 times diluted. Okay, so what would be the original number of equivalence of solute? So let's say the normality of original solution be X. Okay, and the volume of the original solution, that's it, that was V. So now when it was diluted on dilution, we have to calculate so on dilution what will happen is volume of the new solution would become would become 20V. Okay, and this is the normality of 10 ml of the diluted solution. Okay, so we can either write it as either as 10 ml or normality of diluted solution. Okay, and dil. Okay, so we know that normality of diluted solution, which is nothing but n dil, which we calculate in the previous step, would be how much? It is 0.2. Okay, so we can write that this would be equal to equivalent of solute upon volume of solution. Okay, so number of equivalents of solute from here could be calculated with this is the number of equivalents of solute. Okay, now going back to the original equation, wherein we need to find the normality of original solution, which can be written as equivalence of solute, which will remain the same whether we dilute the solution or not, means whether we dilute the solution or keep it in the original form, divided by V. Okay, so the normality of the original solution would be 4. Okay, so now what we can do is we have to calculate the volume strength of H2O2. So volume strength of H2O2 is nothing but normality of the solution divided by 5.6, that would be equal to 4 upon 5.6 ml. Why it's ml? Or rather, you can write it in the form of I've just written it opposite. The normality of H2O2 is actually normality of H2O2 is equals to volume strength divided by 5.6 divided by 5.6. So from this we can write that volume strength would be equal to 4 into 5.6 milliliter. Why it's milliliter? Because here also we have calculated this on the basis of milliliter. So this volume was based on, this was in liter, but when we calculated, when we saw the original solution, this was in milliliter, 20 milliliter. And also we took 10 ml of this dilute solution. So from here the unit flows. Okay. So at the end also volume strength would be upon 5.6 milliliter. So n original was also 4 into 10 to the power minus 3. Okay, because this volume was in milliliter and normality is calculated in liter as we wrote here. Okay, so we have to multiply with 10 to the power minus 3 here. Okay, for this to be in liters. Okay, so for better clarity, let me again write it that, so as this is normality, so this should be multiplied by 1000 here. So the equivalent of solute here would be 0.2 into 20V into 10 to the power minus 3. Okay, so this is the into 10 to the power minus 3 was here. Okay, divided by V. So V and V get cancelled. So the normality of original solution is 4 into 10 to the power minus 3. Hence, this would be 4 into 10 to the power minus 3 in liters, which I directly converted to suit 10 to the power minus 3 into 1 liter is 1 ml. Hence, I directly wrote 4 into 10 to the power minus 4 into 5 into 4 into 5.6 ml, which is nothing but 22.4 ml was the volume strength of H2O2. So with this, we come to the end of this lecture. In the next lecture, we'll be seeing some more questions on the same. Till then, good luck and goodbye.